Okay, let's unpack this. We're stepping right to the, I guess, the deepest edge of scientific machine learning. We're talking about applying neural networks to physical data,
Yeah.
molecules, proteins.
Mhm.
And when you're working in 3 dimensions with real physical objects, standard models just slam into this huge wall. And that wall is rotational symmetry.
That's the key challenge, exactly. I mean, think about it. If you rotate a molecule in space, its physical properties, like its energy, shouldn't change at all. But if you feed that rotated molecule into a regular, say, a graph network, it thinks it's looking at a completely new input. You end up having to train it on millions of different angles just to teach it something the laws of physics already give you for free.
So it's like the model has to inefficiently relearn physics every single time. A massive waste. Our mission today is to, well, get right to the heart of that problem. We're going to dive into the mathematical toolkit that solves this, specifically spherical equivariant graph transformers, or SEGNs. They build the symmetry right into the architecture.
And once we get that foundation down, we'll see what it unlocks. And that's this truly revolutionary system called O-design. It's being called a molecular world model. It can do all-to-all biomolecular design proteins, DNA, RNA, ligands, all in one framework.
But to really get O-design, we have to start with the language of these geometric models. And that means understanding the difference between invariance and equivariance.
Right, these concepts are the bedrock. Invariance is the simpler one. It just means the output doesn't change when you rotate the input. Like you said, the potential energy of a drug molecule. You spin it, the energy value is constant. It's an invariant feature, a scalar.
That makes perfect sense for things like energy or, I don't know, mass. But what about features that actually describe the 3D shape and forces?
And that's where equivariance comes in. This is really the cornerstone. Equivariance means that if you rotate the input, the output has to change in a predictable way. It has to rotate by the exact same amount in the exact same direction.
Ah, like the force vector on an atom. If you turn the molecule 45 degrees, the force vector has to turn 45 degrees with it.
Precisely. If your model predicts the wrong rotation for that vector, it's fundamentally wrong about the physics. It doesn't get it.
So equivariant models succeed because they enforce that rule. They guarantee that if the input rotates this way, the output must rotate the same way.
Exactly. And that's crucial because molecular systems are governed by physics, by quantum mechanics, which has these non-negotiable symmetries built in. Standard models break that law. Equivariant models enforce it.
Okay, so that brings us to the how. How do you actually bake this rotational physics, the SO3 rotation group, into a neural network?
Well, you have to move beyond just simple XYZ coordinates. The whole foundation is built on representing features as something called spherical tensors. These are features that are grouped by their type or degree, which we call dollars.
Right, so $1 is a scalar, that's our invariant feature.
Yeah.
And $1 is a vector, which is equivariant. What happens when you go higher to whole 2, full 2 dollars?
As dollars increases, the tensors capture more complex rotational information. So 1 into 2 is a quadrupole, 1, 3, through an octuple. The full feature for an atom is often a whole stack of these tensors.
And how does the network make sure this whole stack of features rotates correctly? That sounds like a nightmare to track.
It uses a mathematical guidebook, basically. They're called the Wigner-D matrices. If the spherical tensors are the features, the Wigner-D matrices are the instruction manual for rotation. They're the irreducible representations of the SO3 group. They tell every single tensor type, all dollars, all SU $1, exactly how it must transform under any possible 3D rotation.
Wow, so there's a specific matrix block that only handles the type 1 vector's rotation, and it does it completely separately from the type 2's rotation.
Exactly, orthogonal and independent. But there's a catch. The Wigner-D matrices only work if your inputs are already spherical tensors. So how do you take something simple, like the displacement vector between two atoms, and turn it into these special tensors?
And here's where it gets really interesting. Spherical harmonics.
Spherical harmonics are absolutely fundamental here. You can think of them as like a mathematical prism for rotation. They take that simple 3D vector between two atoms and project it into that stack of spherical tensors that we know how to rotate using the Wigner-D matrices.
So they're like a translator. They take a simple direction and break it down into its core rotational components that inherently know how to behave when the system spins.
That's a great way to put it. They're the building blocks for the geometry. This whole projection process is what lets you build the equivariant kernel, which is the core computing unit, the filter that does the message passing.
So the kernel is this equivariant calculator. It takes features, uses spherical harmonics to understand the geometry, and produces new features. But if you're mixing a type 0 feature with a type 1 feature, How do you combine different types without just shattering the whole symmetry? That sounds like the hardest problem in this entire thing.
It is. And it leads us straight to the second critical tool, the tensor product, and how you decompose it using Clebsch-Gordan coefficients.
Okay, let's slow down here because this feels like where the real magic happens.
I agree. When you combine two spherical tensors, say a type Sator feature and a type of geometric feature from the spherical harmonics, you use a tensor product. And the result is this complex, messy tensor that doesn't transform cleanly anymore. You have to untangle it.
So you've basically mixed two elegantly spinning things together, and now you've got this unpredictable wobble.
Exactly. The Clebsch-Gordan coefficients are the key. They give you the change of basis matrix you need to decompose that messy product back into a clean, organized sum of orthogonal spherical tensors. This decomposition isolates every possible resulting tensor type from the absolute difference, k-lars, all the way up to the sum, k plus Euler.
Can you give us a concrete example of that?
Sure. If you combine two type milli-dollar vectors, so two normal 3D vectors, the product is complex. But the Clebsch-Gordan decomposition breaks it down neatly into three parts. A type all dollar scalar, which is invariant, a new type loadable dollar vector, and a type all 222 quadruple tensor.
And that decomposition is what lets information flow between different types. A type feature can update a type bill feature, and the rotational symmetry holds for every single one of the resulting components.
And here's the power move for the learning part. Once you have those clean orthogonal components, you can apply a unique learnable scalar weight to each one. And since a scalar is invariant to rotation, when you multiply it by an equivariant tensor, the result is still perfectly equivariant.
That's the breakthrough. The physics, the Clebsch-Gordan part, tells the model how to transform things, but the decomposition creates these little rotationally safe slots where the model can put its learnable weights without doing the laws of physics.
It's how you parameterize the kernel. The physics is baked in, and the learning happens with these invariant scalars.
We saw early versions of this in models like the Tensor Field Network, TFN, but things really took off with models like the SE3 transformer. What did adding attention bring to the table?
The SE3 transformer took the self-attention mechanism but made sure every piece of it was equivariant. It computes query, key, and value embeddings as spherical tensors, and this allows it to calculate rotation-invariant attention scores.
So the score itself, how much atom A should pay attention to atom B, doesn't change if you rotate the whole molecule.
Exactly. The score is a scalar. It's invariant. So the model can decide how much weight to give a message based on chemistry and distance, not orientation. And it uses that invariant score to scale the equivariant value updates. It's just so much more powerful than simple message passing.
I have to stop here for a second. We're using incredibly sophisticated group theory and matrix algebra just to make a machine learning model work. What's the trade-off? Is this all prohibitively slow?
That's a fair question. The complexity definitely increases. You're dealing with more channels because of all the tensor types. But the flip side is massive data efficiency. You don't need to show the model a billion rotated examples of the same thing. So the efficiency you gain there often more than makes up for the per-step complexity. For these science problems, it's a trade-off that is absolutely worth it.
Which brings us to the application. So what does all this heavy math mean for real-world science? It enables models like O-design.
O-design is really a milestone. It's a true unification model. It's called a generative world model because it takes the basic chemical units of everything, proteins, DNA, RNA, ligands, ions, and puts them into a single unified token space. The architecture learns from AlphaFold 3, but it's for design, for creation, not just prediction.
A single model that can go from generating a new protein to designing a small molecule that binds DNA. That's a level of cross-modality that used to be pure science fiction. What's at the core of it?
It has a few key parts. There's a pair-former module for the complex interactions and a conditional diffusion module to decode features back into 3D atom coordinates. But the critical piece, the bridge that makes it all work together, is the inverse folding module.
Inverse folding is usually taking a protein structure and predicting the amino acid sequence.
Yeah.
But here it's universal.
Yes. For any generated 3D structure, whether it's protein, RNA, or DNA, this one module generates the chemical sequence, the amino acids or nucleic acids needed to actually form that shape. It's what truly enables the all-to-all design.
The level of control you get with O-design is what really caught my eye, though. It's not just make me a molecule. It's incredibly specific, using masking.
Right. That granular control is a huge deal. It uses 4 different levels of masking. You can start with all masking, which is just free generation, or you can use entity masking, which is perfect for designing a binder for a fixed target.
And what if you want to do something more focused, like engineer a specific loop?
That would be token masking. You mask out a continuous segment of the sequence to scaffold a motif. But the really revolutionary part is the atom masking strategy. This gives you atomic-level control.
What does that actually look like in practice?
The paper gives a great example. To create a very specific active site, the protocol might preserve, say, only the atom that's furthest from the backbone oxygen, and it does that with an 80% probability. That level of precision lets you design things like catalytic sites with a specificity that just wasn't possible before.
And it also has two different modes for the target molecule, the receptor. Why are the rigid and flexible modes important?
They reflect biological reality. The rigid receptor mode just assumes the target molecule is frozen in place. But the flexible receptor mode allows the model to generate conformations of both the binder and the receptor at the same time. This is much more realistic. And crucially, O-design-flex consistently beat O-design-rigid, which tells you that allowing the target to adapt is a better path to a good design.
So let's talk results. What did building on this powerful equivariant foundation actually achieve?
The improvements are, well, they're staggering. In ligand-binding protein design, O-design was 12.1-fold better than the previous state-of-the-art RF diffusion AA.
A 12-fold increase. That's the difference between a 1% success rate and a 12% success rate. It completely changes the economics of doing the experiment.
It really does. And for something like atomic motif scaffolding, which is key for enzyme design, it showed an average efficiency improvement of 37.5-fold.
37-fold?
Yeah. So a computational run that might have given you one or two decent ideas before now gives you dozens, enough to fill a 96 wall plate for screening right away.
And what about outside of proteins, the true test of a world model?
And that's where it really proves the concept. For designing RNA uptamers, it got nearly twice the success rate of a specialized RNA-only model. But the biggest breakthrough might be in designing small molecules that bind to DNA. There's very little data for that task, and it's been a huge challenge.
What were the results there?
The design ligands found plausible binding modes, like binding in the minor groove of the DNA, with incredibly high confidence. The error metric, IPAE, was 1.29. That basically means the predicted structure is accurate down to the angstrom level. It's opening up entirely new areas of drug design.
That's just immense validation. Okay, so let's get to the learner's aha moment, a curious finding from the development that kind of goes against your intuition.
Yeah, this is the part I find most fascinating because it validates the whole physics-first approach. When they were doing conditional generation where you fix some of the atoms, they tried two ways to set up the coordinate frame.
The logical way would be what they call partial alignment, right? You fix the coordinate frame based on the atoms you already know. You give the model a stable anchor point.
Absolutely. That was the hypothesis, that constraints should help. But they found the opposite was true, a global alignment strategy where they let the model freely figure out the coordinate frame for the whole system, even with constraints present. That strategy resulted in a significantly lower validation loss.
So wait, the model does better when it has to solve the coordinate problem for the whole complex itself, rather than being forced into a local frame. Why?
It suggests that the robustness you get from keeping the full SE3 equivariance over the entire global structure is more valuable than giving it a rigid local constraint. By letting the model handle the global rotation freely, it maintains the mathematical purity of the physics. And that leads to a better, more accurate design.
That brings us perfectly full circle. We started deep in the weeds of group theory, Wigner-D matrices and Clebsch-Gordan coefficients, and we've ended up with a system, O-design, that can program the molecular world. Equivariant architectures aren't just an abstract constraint anymore. They're the design principle that unlocks this.
Exactly. The success comes directly from encoding the rotational symmetry of our 3D world into the neural network itself. And if this one geometric bias can unlock design across proteins, DNA, RNA, and ligands, it really raises the next big question. What other fundamental physical symmetries or conservation laws, maybe things like energy conservation or dynamics over time, what else do we need to build into these world models to truly simulate and program the molecular universe?
A universe we're just starting to map. The potential for discovery there is, well, it's basically limitless. Something to think about as we close out this deep dive.